Afternoon, class, or good day, whatever time it is at your end. You are welcome to this final session of our course. And at this part, we'll be looking at probability theory. All right, so we'll go into it and consider some important concepts in there. So this is the overview of this section. We'll look at set theory, probability theory, Bayes theorem. Under probability theory, we'll look at independence concepts, conditional probability concepts, and others like that. Then we'll also come to counting techniques and combinatorial probability. Then we will finish with the probability distributions. We will look at 3 of the discrete ones, and then there's only 1 continuous distribution. So probability is very closely linked to statistics, and it's very much used to make give some understanding into any statistical analysis you may be doing. All right, so let's move on to set theory. Set theory is closely related and foundational to probability theory. So to study probability, you need to understand set theory and various definitions that are in there. We will start with elements. We are saying that elements is a possible outcome of any experiment you may conduct. So if you conduct an experiment such as you take a coin and then you flip it, you are either going to get a head or a tail, right? So head and tail are the elements of the coin flip. So again, an element is any possible outcome of an experiment. What about a set? When we talk about a set, we are saying that it's a collection of 0 or more elements. So if you have a set, for example, this set A is equal to XYZ, we are saying that the elements XYZ are the elements, and together with this curly bracket and the commas in between is indicating that we have a set A. So we use a capital letter to stand in for a set. But the elements in there, if they are alphabet, you use smaller letters. So if I can also have a set of males in your class, that will be a set listing out the names of all males in your class. Let's move on to Venn diagram. A Venn diagram, also known as a set diagram, is a diagram that shows the relationship between a finite number of sets. So we use Venn diagrams to illustrate probabilities and events. As we go along, we will come to a point where you see how a Venn diagram looks like. So it's simply a pictorial show of probabilities and events that you'll be talking about. Now we want to know what a sample space is. A sample space is a collection of all possible outcomes. So in any experiment that you perform, every likely outcome you can get together form the sample space. So for example, with the example of the tossing of a coin again, if you toss a coin, you can only get a head or a tail. There is no other possible outcome you can get. So head tail becomes your sample space together. If you look at an example of flipping a fair die, a 6-face die, where we have the 1, 2, 3, 4, 5, 6 faces, all possible outcome of such an experiment of tossing a fair die once or flipping a die once is 1, 2, 3, 4, 5, 6. 7 is not part. So once you list out 1, 2, 3, 4, 5, 6 in a set, you have listed out together the sample space. Now we want to look at what an empty set is. An empty set is a set that contains 0 elements. So an empty set has no elements in there. So we denote it using this, we call it phi, or we use 2 curly brackets with nothing in there. So whenever you see this or this, we mean that set is empty. So B equals phi means that B is an empty set. C equals this means that C is an empty set. What is an event? An event is a subset of the sample space. So events and sets are quite interchangeable, right? So back to the example of rolling of tossing a fair die. If I tell you that if you roll a fair die, it results in an odd number. The event of rolling a fair die and it's resulting in an odd number. The results you are getting, if you're supposed to list out the elements of such an event, you will get 1, 3, and 5. Remember, 1, 3, and 5 are only a portion of actually the results you'd have gotten if I was just looking for what the outcome could possibly be if I listed out a whole what are the possible outcomes of flipping a coin generally. Now I want to look at what a subset is. So a set D is a subset of E if all the elements in D are also in set E. All right, so this is how we denote subset. D is a subset of E. If D is equal to E, that is, if all the elements in D are the same elements that are in E, then we are saying that D is also a subset of E. So we are saying that every element or every set is also a subset of itself. Okay. All right. So given the sets, any set for the set S of made up of results, what possible outcomes of rolling a fair die once? These are the possible outcomes. We say that we can talk about an event E as event of rolling an odd number when the die is rolled. Now the elements of E, all possible outcomes of E will be 1, 3, and 5. So in this case, we say that E is a subset of S. We are saying that S is also a subset of itself. And again, the empty set is a subset of S because the empty set is a subset of every single set. Now, this set S is a sample space because it contains all possible elements of the experiment of rolling a fair die once. So in essence, you describe the sample space and all of these based on the kind of experiments we are talking about. A Venn diagram typically looks like this. We have a square diagram, and then if it's a two set, if you are dealing with two sets, then you have two circles in there. So we are talking about a Venn diagram where S is a sample space, and A is a subset of S. B is a subset of S. So here will be my set A, set B, set S. So this is how a Venn diagram can look like. Okay. Now there's a concept of union. There's a concept of union. So if A, the set A is equal to 1, 2, and 3, and the set B is equal to 3, 4, and 5. Okay. Then we say that the union of the sets, these two sets, is going to be all possible you put together all the elements to form the union. All right. Let me close it rather, and then create a new one. So we have two sets. We want to now talk about the union, and then intersection. So we have two sets, A being equal to, okay, let me use the letter F rather. Two sets, F is equal to 1, 2, and then 3. G is equal to 3, 4, and then 5. We denote the union as F union G, all right? And we say that this will be equal to, so we want to list out, put together these elements. So we have 1 here, 1, 2, 3 is here, 3 is here, but we need to list it just once. So 3, 4, and then 5. So this new set F union G represents the union of set F and set G. All right. So here we look at the union of F and G as the event of F happening, or G happening, or both of them happening. Because when 3 happens, then both of them have happened. All right. Once again, if F, any two events, D and E, okay, if D is a subset of E, then D union E is equal to E. So say take two events, D is equal to say 1, 2, 3, E is equal to 1, 2, 3, 4. Now, therefore, D union E is equal to 1, 2, 3, 4, which is also equal to E, because you list out every element just once. And note that D is also a subset of E, because all elements in D are also in E. All right. Now, if we talk about the concept of intersection, what we are saying is that the intersection of any two or more sets is the set of elements that are common for each of those sets. So back to F and G, which of the elements in F and G are common to both? It's only 3. So if you look at F intersection G, this is how you represent intersection. It's equal to 3. It can be found in F, it can be found in G. So F intersection G is 3. So if you're looking at an intersection, you're looking at what elements can I find in both sets that I'm talking about, okay? Both or more sets that I may be talking about. Finally, we want to look at under set theory. We want to consider mutually exclusive, the concept of mutually exclusive. We say that two sets are mutually exclusive if they share no common elements. So it means the point of their intersection is an empty set. There's no element that you can find in M and also find the same in N. So M is 1, 3, 5, N is 2, 4, 6, are mutually exclusive sets because there's no element here that you can also find here. They each have very distinct elements. So the very important to note under mutually exclusive is that the intersection of these two sets is an empty set. Now, disjoint has the same meaning as the term mutually exclusive. The two sets are disjoint. They do not have any common elements among them. How about complements? Complement of a set T is a set that contains all of the elements in the sample space, except the elements that are in T. So the complement of a set T is denoted by this T prime or T complement. So what we mean is that if T is a set of odd numbers on a 6-phase die, then T is equal to 1, 3, and 5. T complement then will be equal to 2, 4, and 6. T will be equal to 2, 4, and 6 because 2, 4, and 6 are also part of the sample space of a 6-phase die, but they do not belong to T. So the complement of any set is every other element within the sample space, but does not belong to that particular set. Now, if you look at T intersection, the intersection of a set and its complement is the empty set. The union of a set and its complement is the sample space, all right? So if you can see that T intersection T prime is the empty set, and then T union T prime is the sample space. So please let us take note. So here is the end of the set theory concept. Let me illustrate the concept of disjoint or mutually exclusivity and complement in a Venn diagram, and let's bring this session to an end. So we look at the concepts of disjoint set or mutually exclusive. So two sets A and B are disjoint. They mean that they stand apart. They don't have any form of intersection among them. All right. So we are saying if A is equal to 1, 3, and 5, and B is equal to 2, 4, and 6, these two sets are disjoint. There's no common term. So you draw them separately. When we look at the complements, if you have a Venn diagram like this and you have the set T, that represents even numbers from rolling a 6-phase die. And then this will be 1, 3, and 5. So if you look within the rectangle, all the possible outcomes have been listed. If you roll a fair die, a 6-phase die, you're either going to get 1, 2, 3, 4, 5, or 6. But a set T is the event of getting an even number. So this circle is T, and the entire space outside the circle here, the whole space outside the circle here is T complement, because it contains all elements within the sample space. It contains all elements within the sample space, but are not in T. So we say that T equals 2, 4, 6. T complement equals 1, 3, 5. And the entire sample space is 1, 2, 3, 4, 5, and then 6. So see you in the next session.